There we are. Hi everyone. This is Open Neuromorphic. Welcome to our new event. And today with us we will have Sangyeob Kim, who is a postdoctoral associate at KAIST in North Korea. And he has been working on some amazing digital chips for deep learning inference that as you may have guessed from the video, mix artificial neural networks and spiky neural networks to get some pretty interesting results. And I'm really happy to have him on stage with me. And I hope you will be able to enjoy the presentation as I enjoyed his papers back in the day. So now we'll bring Sangyeob on stage. Hi, Sangyeob. Thanks again for accepting my invitation. And at this point, I will leave the stage to you, with the presentation, and anyone else, please enjoy. Thanks again, Sangyop.
Okay, thank you for your nice introduction. I'm Sangyeob Kim from KAIST, and I will explain the C-DNN and C-Transformer in this talk. This is outline of my presentation. First, I will explain the motivation of mixing ANN and SNN. Second, I will talk about C-DNN processor. Third, I will explain C-Transformer. Recently, many SNN ASICs were proposed to achieve low power consumption for always-on application. Each neuron in the SNN accumulates weight whenever it receives the input spike to increase the membrane voltage. And when this value exceeds the threshold, a post-spike occurs. So it has an event-driven characteristic in which computation is performed in the next neurons only when a post-spike occurs. In other words, SNN requires small number of accumulations compared to CNN, and it can achieve low power consumption. In addition, many CNN to SNN conversion methods were proposed to overcome accuracy limitation of SNN. Previous SNN training cannot achieve high accuracy. However, SNN can be converted from high accurate CNN, which was trained by the backpropagation. As a result, the previous words can generate high accurate SNN, which has less than 1% accuracy degradation compared to the CNN. This slide shows our measurement results for the CNN to SNN conversion. We can also generate high accurate SNN for various datasets such as CyPR10, CyPR100, and ImageNet. However, there is a limitation of SNN for low power processing. The performance of SNN varies depending on distribution of input activation. In the case of distribution A, there are lots of small values, so spikes are sparsely generated by the late encoding. SNN requires additions as many times as the number of input spikes. And when the magnitude of the input is small, the SNN can consume less power because of the small number of accumulations. In contrast, in the case of distribution B, then spike pattern is generated because it has many large values. In contrast, the multiplier for CNN is composed of spatially arranged full adders. In this case, even if the operand is small, a large number of full adders are operated, and the change in computational power consumption for magnitude is smaller than that of SNN. Therefore, there is complementary characteristic between CNN and SNN. For large amount of small value, SNNs with low computational power consumption are useful. And for a lot of large magnitude data, CNNs with low power variation are useful. This slide shows the complementary characteristics of CNN and SNN and neural network inference. Each layer of the neural network has a different input distribution, like this. Layer 3 has a wide input distribution. So low power SNN processing is not possible in this layer due to low spike sparsity. Conversely, layer 13 has a narrow input distribution, and in this layer, low power SNN processing is possible due to high spike sparsity. So we propose complementary DNN inference for high energy efficiency as shown in this slide. For low power inference, workloads are divided by layers or within the layer and then allocated to either SNN or CNN, which can consume low energy. Workload with high spike sparsity is allocated to SNN with accumulators, and workload with low spike sparsity is allocated to CNN with MAC. By C-DNN, we can reduce energy consumption for ImageNet classification with LegNet 18 by 31%. This slide shows the overall architecture of the C-DNN processor, which consists of an SNN processing unit and CNN processing unit. The SNN processing unit is composed of 4 SNN clusters, and each cluster has 8 SNN cores. The CNN processing unit has 4 CNN clusters, and each cluster has 8 CNN cores. And the workload allocator divides the workload of the DNN and allocates it to either the CNN core or SNN core that consumes low energy. And the attention module can reduce the standard deviation of the input distribution to increase the ratio of low power SNN workload. And the skip index generator compares the fold gradient of weight with the skipping threshold and generates an index that indicates which alpha neuron can be skipped in backward stage. And SNN core has the 16-4 spike encoders and 64 LPSRs, 64 by 64 PEs, and other 3 firing logic, global counter, and 64 local gradient units. And each SNNP has an accumulator-based inference unit, and each P has the 9 4-bit register file, which is used for the Aeron cache. And CNN core has 8 by 16 PEs, input memory, input loader, wait memory, and wait loader. And the CNNP in the CNN core has a MAC and zero skipping controller. This slide shows the motivation of CNN SNN workload division. In the input feature map of the DNN, some tiles contain significant parts of the object, and there are many large outliers. In this case, a dense spike train is generated through spike encoding, and the CNN core consumes less power than the SNN core. In the case of tile that does not contain many important parts of an object, the spike sparsity is very high due to a lot of inlier data. And in this case, the SNN core consumes less power because it performs only small number of accumulations. As shown in the left of this slide, the energy consumption of SNN fluctuates up and down along the layers depending on the spike sparsity, which change with each layer. And the CNN shows relatively mild variation. In addition, the SNN shows higher energy efficiency than CNN when the spike sparsity is larger than 97.7%. Therefore, if the workload of each tile is allocated to an energy efficient core based on the trade-off point between CNN and SNN, high energy efficient inference can be performed. To use this characteristic, we propose CNN-SNN workload allocator as shown in this slide. The number of spikes is proportional to the magnitude of data. After the operation is performed in the previous core, the intermediate data for a specific tile is moved to the output memory. At this time, the number of spikes in the tile is obtained by accumulating data in each core, and it is passed to the workload allocator. And then workload is allocated to either the CNN core or SNN core, which shows lower energy consumption. Resonance 18 with ImageNet shows an average of 94.5% spike sparsity, and the energy efficiency of the C-DNN increased by 43.3% compared to SNN and 16.7% compared to the CNN. In addition, we proposed C-DNN optimization with attention to achieve high energy efficiency. The attention map is obtained by the channel-wise pulling on the input feature map and then performing the small convolution with pre-trained weight for the attention. Then it is multiplied with the input feature map to make values of insignificant lesions even smaller. Therefore, spike sparsity increase and the low power SNN core workload increase without the accuracy loss. Moreover, in ImageNet, objects exist only in a small fraction of the 2D image plane so that the attention module can shrink the input distribution. So, for example, the standard deviation of the input feature map in the second layer of Resonance 18 decreased the standard deviation from 0.23 to the 0.09. Therefore, the spike sparsity increased and more workloads are allocated to low power SNN core without the accuracy loss. This slide shows the attention module, which is composed of the max pooling unit and average pooling unit and 8x2 meg array and multiplier. The result of the previous layer is transferred to the this attention module, and it is multiplied to the attention map. After attention, the modified input feature map is transferred to the next core for the next layer operation. The C-DNN processor with attention module operation achieved 97.9% spike sparsity for Resonance 18 with ImageNet dataset and 26.2 tops per word, which is 85.8% higher than SNN and 51.4% higher than CNN. And this slide shows the challenges for complementary DNN processor. The SNN used all input channel for computation in a specific time step, and the same weight should be fetched again in the next time step, as shown in the left of this slide, like this. Therefore, the same weight memory address is accessed multiple times, resulting around 70% power consumption of total inference power. To solve this challenge, we propose SNMP array architecture which can reuse fetched weight data. Each SNMP has an inference logic with an accumulator and 9 4-bit Aron cache for temporal weight leaves. Then the spike encoder converts the input data of the pre-neuron to the spike train, and the generated pre-spike is transferred to the SNMPs in the same row by the broadcasting. And this slide shows the operations of SNMPE with Aron cache. Before the SNN operation, the weights for the 9 pre-neurons are fetched from the global L2 cache SRAM to each Aron cache. The Aron cache is lestified. At cycle 0, the spike of the pre-neuron 0 is transferred to the SNMPE. So the weight corresponding to the pre-neuron 0 is selected by the index from the spike encoder, and the weight from the Aron cache is accumulated with a partial sum. At cycle 1 and cycle 2, the SNMPE does not receive the spike from pre-neuron 1 and pre-neuron 2. In this case, the weight lead operation and accumulations are not performed by clock gating for power reduction. At cycle 8, the spike operation for the pre-neuron 8 is performed in the SNMPE. During a cycle, all spikes for all pre-neurons connected to the post-neuron can be transferred, and the weight accumulation in the first time step can be completed. After that, the adder tree generates the membrane voltage by a column-wise operation of the PEs, and the firing operation is performed. After one time step operation, at cycle 9, the pre-spike of the next time step are transferred to the PEs, and the weight in the error cache are reused instead of the SRAM access. Therefore, SNN core performed only one data fetch during the 10 cycle. This operation is repeated and the weight in the add-on cache are reused until the last time step. So we can eliminate the redundant SRAM access during the SNN operation. And this slide shows the performance with distributed add-on cache architecture. By eliminating the repeated SRAM access, the reusability increased by 3.3 times and 5.5 times for ResNet 18 and MobileNet with ImageNet classification, respectively. Moreover, the power consumption of the SNN core decreased by 42.2% and 49.1% for ResNet 18 and MobileNet, respectively. And this slide shows the chip photograph and summary table of C-DNN processor. It integrates the SNN core and CNN core and supports SNN single mode, CNN single mode, and C-DNN mode. The C-DNN processor can achieve 24.5 TOPS per watt for ImageNet classification, and it can achieve an energy efficiency of 18.5 TOPS per watt and 16.7 TOPS per watt for CyP10 and ImageNet training respectively. And this slide shows the results of the inference benchmark test with the C-DNN processor. For the ImageNet classification with ResNet 50, the C-DNN mode can achieve higher performance improvement by the attention module. And the C-DNN mode increased the energy efficiency by at least 31% for ResNet 18 MobileNet compared to the CNN SNN single mode at the same condition. And this is a demonstration video for C-DNN. This is a C-DNN processor and the chip photograph. And this is our demonstration system. First, I will show you the object classification with C-DNN processor. This is the camera preview, and the workload of the input image is divided by the SNN and CNN for C-DNN processing. When we click the C-DNN mode, the layer-wise, the CNN and SNN workload division layers are shown. And this is object classification on video clip. The left is the CNN mode, and second one is SNN mode, and third one is C-DNN mode. As shown in this part, the C-DNN mode, the workload is divided by the SNN and CNN, and it can achieve the lowest power consumption compared to the CNN and SNN. This is the power consumption comparison results. As a result, the C-DNN can achieve the optimized power consumption. And this slide shows the comparison table of C-DNN processor. The C-DNN processor can achieve 53.1% higher energy efficiency compared to the previous state-of-the-art inference processor. Moreover, it can achieve the 60.7% higher energy efficiency for ImageNet training compared to the previous state-of-the-art. And next, we explain the C-Transformer, which is proposed for extending C-DNN to realize ultra-low power on-device large language model system. Yes, first we try to adapt the C-DNN to the on-device large language model. Recently, the large language model is widely used in server for various language tasks such as translation, summarization, and Q&A. And now, on-device large language model is strongly required for privacy, personalization, and cost issue. And the mobile device requires the low power consumption because of the battery limitation issue. However, realizing low power on-device LLM is really hard because LLM requires 47 times computations compared to conventional DNN, which is used for image classification. To solve this problem, we tried to adopt C-DNN for on-device SNN to solve the computation overhead. And this slide shows the challenge of adopting the C-DNN for on-device SNN. The first challenge is that the high recomputability is required. The SNN requires only accumulations and DNN requires MAC operations. So if when we design heterogeneous architecture, the co-utilization can be dropped because the ratio of the SNN-based transformer and DNN-based transformer are dynamically changed. This slide shows the ratio of spiking transformer and DNN transformer for each layer and each model. These results are measured by using our C-DNN workload division result, which I explained in the earlier slides. In the case of language modeling with GPT-2, the ratio of spiking transformer varies from 45% to 98%. And in the case of translation with NT5, the ratio of spiking transformer varies from 48% to 99%. So the ratio of SN mode and DNN mode is different for each layer and each model. So we propose the configurable homogeneous DNN transformer and spiking transformer core to increase hardware utilization. This slide shows the overall architecture of the C-Transformer. It has 48 homogeneous DNN transformer and spiking transformer cores for high co-utilization. And weight generators are integrated for high external memory access power reduction. In the homogeneous DNN transformer and spiking transformer core, the hybrid multiplication and accumulation units are integrated. And the hybrid multiplication and accumulative unit has right part full adder array and left part full adder array and the reconfigurable connection. In addition, the output spike speculation unit is integrated to support output spike speculation for low power spike domain processing. And this slide shows the detailed architecture of hybrid multiplication accumulation unit. The left of this slide shows the conventional multiplier. To perform multiplication, the different input bits are transferred in the different direction, and the same multi-bit weights are allocated in the vertical direction, like this. However, the hybrid multiplication and accumulation unit should perform both multiplication and accumulation. So the configurable connection is inserted into the conventional multiplier to reconfigure the hardware into the multiplier and accumulator. The hybrid multiplication accumulation units support two different modes. In the DNN transformer mode, one multiplication between one input and one weight can be performed for deep neural network. In spiking transformer mode, multiple accumulations between end operation result of different channels can be performed, like this. In DNN transformer mode, one multiplication should be performed as shown in this slide. So the different bit of the input is transferred in the vertical direction, and the same weight is broadcasted to the vertical direction. In this case, W0 is broadcasting to all lows. And then the carries of the right part are transferred to the left part. So the weight and input data feeding and configuration are same with the conventional multiplier as shown in the simplified diagram, and it can perform one multiplication for DNN. And let's move on the spiking transformer mode. In the spiking transformer mode, the different channels and operation results should be accumulated in the column direction. So the weight and the spike train is unicast in the vertical direction. So each row receives the different spike from the different channels, and each row receives the different weights from the different channels. As shown in the simplified diagram, each low receives the weight and spike train of each low, and each low computes the end operation result of each channel. Like this, the first channel computes the end operation result of the zeroth channel, and the first low computes the end operation result of the first channel. However, there is problem to accumulation in the column direction. The bit position of the end operation result of different low are different, like this. So the bit alignment is required for accurate accumulation because in this case, the different bit position is allocated in the column direction. So in step 2, the weight bit position alignment is performed. For example, in the case of second low, like this, the original bit order is 3, 2, 1, 3, 2, 1, 0. But after alignment, the bit order is changed by 0, 3, 2, 1. By alignment, the same bit order is positioned in the vertical direction. For example, in this column, the every third bit of the different weights are allocated in the same column direction. So, for example, in the fourth column, third bit of the different weights are assigned in the same column direction. So, by the alignment, we can accumulate in the column direction correctly, like this. After that, the higher bits are allocated in the right part, and the lower bits are allocated in the left part. So, the right part computes the higher part of the partial sum, and the left part computes the lower part of the partial sum. To aggregate two parts correctly, the connection between two parts is disconnected. And the left shifted right part result is aggregated with the left part result. Finally, the carries of the right part are added into the aggregation result to generate complete accumulation result. To sum it up, the DT mode computes the one multiplication by using only one weight, and SE mode computes n accumulations by using n weights. So there is weight bandwidth unbalance between two modes. And this slide shows the result of hybrid multiplication accumulation unit. We can increase co-utilization by from 32% to 36% for various benchmark tests compared to heterogeneous architecture, and the energy efficiency increased by 59%. And this slide shows the motivation of output spike speculation to reduce energy consumption of SN mode. The late coding makes the input spike probability is proportional input magnitude. So it has the special features that the input spike rate in the sample time step can tell the input spike rate of entire time step. And the input spike ratio in the sample time step can predict the input spike rate of the entire time step. By the special feature of input rate coding, the output spike rate in the sampled time step can tell the output spike ratio of the entire time step. So the output spike of the entire time step is similar to the output spike ratio in the sampled time step. So the output spikes of the entire time step can be speculated by result of the sampled time step. So we propose output spike speculation to reduce computation energy of spiking transformer by skipping integrate and fire operation. So we propose output spike speculation with sampling. In step 1, the input spike encoding with late coding is performed for different channels. In step 2, the integrate and fire operation with only sample time step is performed. And then the output firing probability is computed, like this. In step 3, the output late coding is performed with the computed output firing probability to speculate output spike pattern of the remaining time step. Finally, integrate and fire operations for remaining time steps are skipped by speculation. For example, in the case of output spike speculation as shown in this slide, the 25% sampling ratio is used and integrated final operation for 75% time steps are skipped. And this slide shows the output spike speculation unit architecture and performance. The output spike speculation unit includes the probability sampling unit and the speculation unit to perform sampling and speculation. As a result, from 57.9% to 59.3% time steps are skipped for various benchmark tests. And it supports various tasks such as language modeling, translation, and summarization. The C-Transformer used integer 8-bit precision in homogeneous DNN transformer, spiking transformer core, and some outliers in inputs are handled in 1D SIMD. For GPT-2, MT5, T5, and FSMT, our chip shows 0.21 to 0.33 times computation energy reduction. This slide shows the chip photograph and summary. It can support both DNN transformer and spiking transformer. It achieved from 22.9 to 47.8 TOPS worth of energy efficiency and 50 MHz, 0.7 volts. And it achieved from 2.6 to 18.1 microjoule per token of system energy consumption for various tasks such as language modeling, translation, and summarization. And this slide shows the comparison table. With a DDR3 interface, our chip shows only 18.1 microjoule per token of system energy consumption for GPT-2 large model with 708 megaparameters. So we achieved 30.2% lower energy consumption than the previous state-of-the-art, even though our model has 2.1 times more parameters. Moreover, it consumes 72.2% less energy with similar number of parameters. And this slide shows our demonstration video. This is the C-Transformer and chip photograph. And this is our platform. We can support 3 types of language task. And this is the summarization task. This is the input text. And we type the input text like this. And after click the start button, the output is shown in the result part by processing our C-Transformer. And this is the workload division result. And this is the DNN mode, and this is SN mode, and this is our hybrid mode. And this is the power consumption result. So our hybrid mode can achieve optimized power consumption. And this is Raspberry Pi and Jet Nano, and this is our C-Transformer. And this C-Transformer can achieve the highest throughput compared to others. And then now my presentation is end, and if you have some questions, please ask me.
Thank you so much for the presentation, Sangyeob. It was really, really interesting. So I have some questions, let's say. C-DNN was targeting mainly static image processing, let's say. Have you and your research group considered taking advantage of your, let's say, dynamic scheduling approach that you have right now, based on attention to event-based cameras, which would relieve you of the burden of having on-chip encoders to spikes and to automatically have per patch activity in the input frame?
Can you tell me again?
Yeah, sure. So basically, in event-based cameras, you have events instead of having static pixels, no? And only active pixels provide events at the other end of the camera, let's say. I don't know if you are familiar with the concept of event-based cameras.
Okay. Actually, my work is related with the RGB camera. Yeah,
Okay.
and we use the input image. But I think we can adopt our approach to the event-based camera because the event cameras um, uh, in my knowledge, the event camera gives the inputs to the processor when the object moves fast or object moves dynamically. So in this case, the event camera transfer a lot of data to the chip. So in this case, the neuromorphic computing methods can uh, consumes a lot of power because of a lot of accumulations. So I think in this case, the uh, first accumulating the events during the some cycles, and after that, competes with the DNN can consume less power. And in other case, the object does not move fast or does not move dynamically. In this case, the event not uh, occurs dynamically. So in this case, the accumulator-based neural computing can consume less power compared to the DNN.
Okay, thank you. Thank you. Okay, and I was wondering, also regarding CDNN across the various networks, more than benchmark on ImageNet, which was the utilization of an SNN core? So, how much were you offloading to CNN to artificial neural network with respect to the SNN cores across
Uh,
the set of networks you were considering?
um, yes. Yeah. Actually,
On
the
average,
workload.
not an exact number, yeah.
Yeah, workload. The ratio of workload is changed by the which network we use, but when we assume the layer-wise the workload division for the VG16 for CIPA 10, the workload ratio division result is shown in this figure. The first layer and the 10, 11, 12, 13, 14, 15, 16 layer is allocated to CNN, and this is worked for the CNN core, and other layers are allocated in the SNN core. But in this case, when we processing the uh, when if we compute the C-DNN, the utilization of the heterogeneous core is very important. So in this case, the layer-wise workload division can cause the utilization drop. So in this case, we use the layer-wise parallelism. So in this case, we unload the multiple layers in the CDNN processor to handle the utilization drop. And also, but this can not solve the actual problem. So we propose the C-Transformer, which integrates the homogeneous CNN and DNN core. So in this case, this slide shows the workload ratio division results of each layer. In this case, we does not use the layer-wise the workload division. In this case, we divide the workload of the DNN and SNN in the one layer. So if we compute the one layer, we divide the workload by the CNN and SNN by selecting the each data. So in this case, the utilization drop is very, very serious. So we propose the homogeneous core like this. So this homogeneous core can compute the DNN mode or SNN mode. So we can eliminate the utilization drop by that issue. Yeah.
Okay, thank you. And regarding C-Transformer, from the model itself, what did you rely? What kind of techniques did you use to switch the model of the transformer itself from the conventional one to a spiking domain one? And what I mean by from a purely PyTorch perspective, for instance, did you do some
Yeah,
model evaluations or?
yeah. You mean that how can we generate or targeting the model for Neuromorphic computing, right? Yeah.
Yes, the spiking transformer model. What did you use actually? That's what I was interested in.
Yeah. In this case, actually, the training the large language model is really hard because of the it requires large sentences or large data sets. So we think the actual training is that uh, it is very hard. So we use the previous pre-trained conventional transformer. And first, we download the conventional pre-trained transformer in the Hugging Face platform. And then we adopt the CNN to SNN conversion for that model. So we generate the SNN model, yeah, with high accuracy. So after that, we select that two models share the weight. So the weight parameter is not really big issue. So just we select the most of the core. Yeah. So we use that techniques for the benchmark test. Yeah.
Okay, thank you. Last question. Do you think that the speculation mechanism that you adopted in C-Transformer could be adapted also to conventional transformer architectures? Because, for instance, on the model level, what it is done is mm, to let's say to stop the computation on certain tokens in stop computing the attention on certain tokens from a model level, but from a model level it's easy. Let's say in hardware it's much more complicated. Do you see any adaptation of this speculation mechanism beyond the spikes to purely, let's say, CNN computation? For instance, I cannot attend I can speculate that I will not need to attend those tokens to predict the next token, for instance.
Um, you mean uh, actually your question is about the output speculation, right?
Yes. What I meant is at a certain point you will speculate how many spikes you will have in the next time step so that you do not have to actually compute to generate them,
Yes,
right?
right. Yeah, right
And
there.
do you think this is a concept that could be extended in hardware to attention computation from artificial neural network perspective, which means I can speculate that I do not need to attend all the tokens. I do not need to multiply by all the rows in the matrix to predict the next token, for instance.
Yeah, actually, it can be adapted, but in our case, we
Yeah. I
does
mean, in
not.
the future, not not
Yeah.
the exact in silicon, of course. Yeah.
In this case, we that adapts, but actually, the token is uh, the word, right? But in that case, the actually um, we our words are very related. Yeah, and so it means the first token and second token has very strong relationship. So maybe the input embedding of the tokens can be similar. So actually, I think this feature can be adapted for the language model, as you mentioned about. Yeah.
Okay, thank you. There is a question from the audience. I don't know if you can read it on the screen. Are you able to see it on the screen? Do you want me to read it?
Yeah. This question is about could you elaborate more at why you want to convert from CNN to SNN, right? Yeah. This is for supporting the SNN computing methods. Um, First of all, the SNN network training method is cannot achieve high accuracy. There are so many SNN training methods such as the STDP or BPTT, but this method cannot give the high accuracy. Even if and moreover, in these days, the large language model training is very hard. So the SNN conventional SNN training method cannot achieve the high accuracy. So we want to make the high accurate SNN for the large language model. So our choice is just one, the SNN to SNN conversion to achieve the high accurate SNN system. So I think this is very necessary for the large language model system with the sparking neural network.
Okay, perfect. Thank you. Oh, let me see if there are any other questions. No, it seems not. So at this point, I would like to thank you for the talk. It was really interesting. Anyone that is more interested in these works, you can find the papers on our event post on LinkedIn, or you can reach out to Sangyeob via email if you're interested in. And thank you very much, Sangyeob, for agreeing to present for us. And I think we can wrap it up here.
Okay, thank you for your invitation. Yeah.
Thank you very much. Have a nice day. Bye, everyone.
Yeah.